Hi there. So in this video I want to talk and build on our expression for work and how we can talk about what assumptions are kind of present, how we can talk about it a little bit better. I want to pick up where we left off last time. And I want to explore this left-hand side a little bit more. Right now, what we've done is specified that the force is in a certain direction, and I am moving in that direction. Right? So the force is applied in the direction that I'm moving right now. And that's all well and good, but we need maybe something a little bit more general. And the best way that we can probably write this is that, I'm getting ahead of myself. What if we just consider a scenario, right? Not the same scenario as pushing the block along the track. We're going to take an offside kind of view of that in a second. But what I want to consider is, what if my force is not pointed in the direction of my travel, right, of my motion? Does it change that motion, right? And we know it does. It doesn't speed it up or slow it down. We know that if it's perpendicular, I would actually start to go in a circle, right? So the direction here of my force actually matters when I'm thinking about the change in kinetic energy if I speed up or slow down. Right? Remember, kinetic energy is not a vector, it's a scalar. So the direction of my object isn't factored in when I think about kinetic energy. So I need to kind of talk about the directional aspect of my force versus how I'm moving. And the best way that we can do that is to actually employ the dot product. So I can best write work as equal to the path integral. And you can write this a couple different ways. I'm just going to write it as a little p at the bottom. But basically all I'm saying is I'm going along a path, and I need to just consider that, right? If I'm starting here and I'm going along a path like this, and this is my end, so start, end, I can talk about the force along that direction, right? Dot it with the actual element of my path. And that element of my path always points tangent to my path. And it's a very small element, right? Of course, we're integrating here. We have infinitesimally small elements here. But what I'm allowing for is that my dl is actually changing direction as well. Now, this is the most general way that we can talk about work. More often than not, we're going to say the force that we're considering is constant along our path. And we're also going to say that the force is not spatially dependent, right? What I'm going to say here is that F is not a function of L or dl or x or y or anything like that. I'm just saying that I have a force in a direction, and I'm going to dot that with whatever element of displacement I have. Generally speaking, in this class, we're only going to have a single direction of displacement, or a constant direction of displacement. We might move in x and y, but we're not going to be moving parabolically right off the bat. So more often than not, we can just say that f dot dx or f dot delta x is going to be our work. Some situations we'll actually write f dot d, which is just to say our displacement, our distance traveled. That's perfectly fine as well. If you have certain conventions that you're comfortable with, go for them. But this basically starts to pick out the direction of f parallel to the direction of dx or delta x. And remember that we can write our dot products as a simplified kind of expression. We can say f dot delta x is actually f delta x times cosine of the angle between them. I'm going to talk about this a little bit more next video, but I want to take a little bit of a moment and think about this. If f is constant, then I also have a path independence here, right? I have something with what's called a conservative force, right? Conservative forces are like gravity or electrostatic interactions. We're not talking about that in this class, but gravity is a conservative force, right? It's path independent, which means it does the same amount of work whether I fall straight down or whether I go around some like helical kind of structure, slide or something like that. Gravity does the same amount of work in both of those situations. The path does not matter. Non-conservative forces are when the friction, well, I've just given it away. The example is friction, right? Non-conservative forces depend on the path that we actually go. It's not path independent. So friction matters because how far I actually go, any sort of amount of distance I go, not displacement, distance, right, actually gets factored into how much work friction is doing on my system. So these are two kind of different types of forces, conservative forces and non-conservative forces. We're going to see in a little bit how that kind of plays into energy transfer and energy transformation within their system and within the environment around it. So I'm going to leave it here, keep this video a little bit shorter. Next video we'll talk a little bit more about the dot product, and I'll see you then.